Hey guys, we're going to talk about section 11.2, which is curves, polygons, and symmetry. And I'm just going to go through some content with you guys, make sure that you're getting the ideas. I'm going to do it as quickly as possible again. So the first thing we want to talk about are all of these terms up here. So we're given different curves, and we're going to talk about whether or not they are simple, closed, a polygon, convex, or concave. Now these two right here, I'm including in this table and I'm going to describe their answers, but I'm also going to give you a separate slide on that. So if what I'm saying here doesn't make sense, hopefully the next bit of information about it will clarify some of that for you. So this one right here, this curve, we would call this simple because it just is just the basic run-of-the-mill curve that you've got. It has a shape, and that's it. Okay? But this one right here, well, not but this one. So the term simple can basically be applied to any figure that you're given. Okay? Um, and then closed, however, hopefully you guys can tell, this is not closed. It does not have a point that cycles around in some way, either in figure shape or in some other way. This doesn't close. This one here does not close because of this empty portion. But this figure that you see here, there's no opening to it, so that is closed. Same for this figure here. Now, polygons need to have, so let's talk about the definition of a polygon, which is why I have this table here. Polygons need straight edges. They will meet, the edges will meet at vertices, and it must be closed. It must also be simple, which, let me clarify my definition of that, because I was super vague. Something that is simple does not have any crosses through it. So this is simple. This is not, because it has that cross through it. Okay. So these figures are, none of these figures meet all of these qualifications, so there are no polygons in these four. I'm going to give you some more in just a minute. Now, convex and concave. This figure here is neither because it's not closed, and the same holds for this figure here. If they're not closed, then they need, then you can't even talk about this. I'm saying closed. Let me just click undo instead. Convex / concave, those need to be closed. Okay, just a moment. Let me pause my video. Okay, so neither of these can qualify as either convex or concave. But this figure here, sorry, my phone is going off. This figure here, the third one, so let's name these. This is A, B, C, and D. C is a closed figure, so we can talk about whether or not it's convex or concave. Now, for something to be convex or concave, basically means that if I drew a line through it, so I'm just going to do a version of the figure that we have, that if I drew a line through the figure, so I'm sorry, I put that in the wrong spot. Okay, if I draw a line through it, I'll do a line in a different color, and I'm just going to do a random line. There's another one, there's two, there's three. Okay, so we're going to look at these three lines separately, but essentially, for any line drawn through the figure, it crosses through the exterior points, and it should not cross through anything else but interior points. But the thing is, this line here crosses through those two interior points, or those two exterior points. So basically it goes into the interior, and then it goes to the exterior, and then it goes back into the interior. If a line does that for any figure, so it does that here, interior, exterior, interior, then that means that it is concave. Okay? And an easy way to think about that is that anything that is concave has a cave. So this is a cave right here, this is a cave right here, this is a cave, any sort of indent whatsoever, even if it's super tiny. Imagine if an ant can shelter in that cave, then it is concave. So a convex figure would look like, let's see, how can I do a convex simple figure? That's not a polygon. I honestly can't, oh, not a polygon. There you go. So this figure right here, please ignore that extra indent. That's supposed to be just simple. There we go. So if I drew a line through it, let's do that in a different color again. That crosses through an, oh, sorry, I gotta go back to pen. That crosses through an exterior point, and the whole time between those two exterior points, it is all interior. Which means that, and there's no line that I could draw through here that would do anything except stay in the interior. So that's why this is convex. So part C is concave, part D is convex, because there's no line I can draw there. That won't go through the interior only. All right, so I'm going to add a page to this. I guess I can't add pages because I'm not logged in here. Sorry. Let me just clear this page. Okay. Oh, you know what? Let me give you a second before I clear it. So I like to give 3 seconds. Pause it, get what you need, and then when you unpause it, I'm going to erase everything. Okay. So we can do one more table to show this stuff. So I'll give you a curve. Let's go with this. Imagine those are straight lines. That's just, I should give you straight lines and not try and make you imagine it. I mean, that's the whole point of doing this kind of stuff on the computer, right? Is that you want it to be more accurate. Okay, let's close in that point. Yeah. All right, so that's one figure, and then let's do another figure. All right, let me close that in. Okay, and let's do one more figure now. Let's close that in as well. Okay, that's supposed to be just a close point there. Okay, so first of all, we want to talk about whether or not it is simple. Well, this figure has a cross. It has two totally separate interior spaces. Like, if I tried to do one of those fill kind of things to color it, so if I tried to use the little dropper to color everything here, it would only cover one section, and there's a totally separate section, so this is not simple. However, these ones are, because there's only one interior space. Let's talk about whether or not it's closed. So this figure here, I'm sorry, well, all of these figures, I made a very specific point of closing in all of them. There are no openings. Okay. Let's see. The next one is whether or not they are polygons. Okay. This one here, because it has two separate spaces, that's not a polygon. This one and this one, yes. They are simple, they are closed, they are all straight edges, they meet at vertices. Those are polygons. We're good. Okay, the next part is whether or not it is, oh, my hand just slid there, whether or not it is concave or convex. Let's go concave first. Does it have a cave? Or the more appropriate way of figuring this out is, does a line that crosses through and oh, let me do that in a different color. Does a line that crosses through from the exterior of one side to the exterior of another, does that always stay in the interior? So we've got an interior section here. This is all interior. But then this section right here, that's exterior. And then we have another interior section again. Well, that's not good. That means that this is not convex, this is concave. And you can see it has a cave right here. Okay, so it's like this is the opening of the cave right here, and you can cross through. A little ant can go in here and hide in the rain. I don't know, I'm just trying to make it very clear for you guys. Concavity is something that really confuses students so often, even though it's as simple as that red line right there. Oh, what? Oops, I just keep going for some reason. Do that red line one more time. It's right there. It's as simple as does it cross through the sides more than twice? If it does, then it's not convex, it's concave. And the thing is that we want concave or convex shapes because concave shapes, they don't fit a lot of the properties that we are trying to define in geometry. I mean, there are other properties for concave figures, just not ones that we talk about at this level. All right, this one here, if I drew a line through the sides, it would not ever cross from exterior to interior and then more than once. It goes through one edge, interior, the other edge. That's all that's going to ever happen with this figure. So this is not concave, this is convex. Oh, jeez. Okay, and then this last figure, if I, let's see. You know what, guys? I just thought about it. I'm treating this as if that was a full figure. Since it's not simple, I don't even really need to talk about concavity. I'm so sorry. That might be confusing. That's not a necessary point. When it's not simple, you don't need to do that. When it's not closed, you don't need to do that. And I'm not going to ask you to do anything like that on the exam, so don't worry. That's not going to be something to bother you guys. All right, so this one is convex. And this one here, hopefully you guys can guess. I did a line through it. Right there. That's exterior. Interior, exterior, interior. Doesn't work. So this one is concave. It has a cave. All right. Get that down. We're going to switch to another blank page for a second. And I'm going to emphasize more of this interior, exterior stuff. Okay, this is kind of a funny thing to look at, but the idea of talking about the interior and exterior is made easier when you see these really strange pictures with these curves, because you have to ask yourself, so I put a point in each of these, and we'll just call this point X. So we want to know, is point X in the interior or the exterior of each figure? So I'm going to give you guys a second. You can pause the video, take a look, and see if you can determine without tracing the image and then drawing a line to it. When I had my students in class do that, they all just drew lines to the stuff, and they weren't really thinking about whether or not like there was a strategy to it. And the real test of whether or not you can do this is this one right here, because that's the hardest, I think. So take a pause. Think about how can you find where point X is. So let me write the question down. Is point X in the interior or the exterior? I'm going to give a 3-second pause. Okay, let's talk about this. So, it turns out that there's a pretty easy strategy for this, and it's very much like what I've already shown you with the convex and concave stuff. So if you draw a line, and this line can go through any part of the figure, I'm just going to pick from here to here, okay? If you draw a line and count how many points it goes through, or how many times it goes through the edges, you can figure it out, okay? So let me draw a line for each of these figures. Let's go this way. And let's go this way. Make it difficult for ourselves. Let's go this way. Okay. So the next thing I'm going to do is I'm going to count how many times it crosses through the edges. So let's see. Oh, I need pencil or pen. And let's do a different color. Let's go with something bright. Hopefully that's bright enough. 1, 2, 3, 4, 5, 6. So this one crosses through 6 edges. This one, 1, 2, 3, 4. You might not be able to see those, but those are teeny tiny. 5, 6. I did not plan that at all. And then 1, 2, 3, 4, 5, 6, 7. Then 1, 2, 3, 4, 5, 6, 7. Wow, that's weird, guys. I swear. This was all really random. Anyway, so I'm going to now pause the video and I'm going to go through and actually show you with the strategy that my students in my class did, whether or not these are in the interior or the exterior. And then hopefully you guys can come up with a pattern from there. So let me pause it real quick. Yeah. Okay, this looks like a mess, but the only way I could think to show you guys without the drawings being really confusing was to shade these parts. So bear with the really ugly pictures. So these two, when I determined whether or not they were in the interior or exterior, they were exterior, and these two were interior and interior. And I know it's tough because the numbers ended up being really, really very, they were too similar. So, of course, these two would be exterior and these two would be interior, or vice versa, because they're the same number. So let's take a look at another number then. I'm just going to drag in the PowerPoint that I'm using, which is the textbook PowerPoint that you guys have on Blackboard, but it's because I'm trying to run through this as quickly as possible. So if you look at this region that they gave you, I wish I could draw on this. I think I can. Let's see. How can I draw on it? Let me pause the video real quick. Okay, so I went through and drew a line. Oh no, I just moved it. Undo. Okay, I drew a line and then I drew in points to really illustrate all of the edges that we crossed, and I ended up with 10 points. And you can see from the shading in this image that that is on the outside. So that means that, let me get this out of the way, sorry. That means that when we had even numbers, let me do another slide here. So when we had a 6, we were on the outside, or the exterior. When we had a 10, we were on the outside, or the exterior. When we had a 7, we were on the interior. Sorry, my handwriting is so bad here, guys. My pen has been giving me trouble lately. Well, that's still not, I mean, that's, my handwriting is still bad anyway. Anyway, so I will give you some other numbers. So if I had 4, I'd be in the exterior. If I had 9, I'd be in the interior. So essentially what happens is If I cross two lines, I am crossing through my interior, from my exterior through the interior all the way back out. So I'm always going to be on the exterior. If I had 3 lines though, I used the wrong color, then I am crossing through, so let me show you my 3 lines. Then I am crossing into my interior, back out my exterior, and then I cross my exterior back in again. So I end up back in the interior. So what happens is when I have even values that I cross, or an even number of sides that I cross, then I'm in my exterior. If I have an odd number of sides that I cross, then I am back in my interior, which makes sense because if you're crossing one side, then you're definitely on the inside because you've only gone through one side. It's like going through a door. You're in a room. If you go through another door, you're back out of the room. That's all this is, okay? And this is an easy way to connect interior, exterior with concavity. Okay, your textbook likes to, a lot of textbooks like to give in definitions of concavity that have to do with a figure and all of its interior angles. So like this is an interior angle. And it says, your textbook's definition says that all interior angles must be less than 180 degrees. So like every angle is less than 180. But if you look here, that's a straight line. That's 180. So it's definitely bigger, which is why it's concave. But that definition, you had to talk about the angle measures, you have to see that. And while that is something that you guys need to be able to understand, I want you to have this understanding of concavity as well. Okay, let me pause the video for just a second. All right, a note on the resource that I'm going to be using right now for the next couple of big properties. This website that I'm at, GeoGebra, is a tool that was designed as a free resource because there was a different resource that some schools were able to afford and were able to give to their students. And students in schools like the ones I've taught at and the ones I went to when I was a student couldn't afford those things. And so some really great computer programmers created this manipulative website. I love it. I've used it a lot when teaching, and when I'm teaching high schoolers, they're really open to what this website can do. When I have tried using this at y'all's level in this class, students reject it because it's not something that a lot of you guys have learned to work with before. And so I want you to keep an open mind, and I would highly recommend that you, in your spare time, go play around with this. If you have children in your family that are learning anything to do with geometry, this is an amazing tool. And the person that I'm using right now, this Tim, I don't know how you pronounce his name, for years I have sought out his resources because they are clear, they are short, and they are everything that I expect my students to be able to understand afterward. So if you have time, go to GeoGebra, look up this person. His resources show up in a lot of different topics. He made all of these tools. I think he actually does this for a living, like working with GeoGebra, and that's part of it. But as us just free viewers, you should really give this a try. And so I'm going to illustrate, let me click here for a second. We're going to be looking at the interior angle sum of convex, meaning they don't have the caves, polygons. This is my symbol for angle for those of you who have not watched the 11.1 video. And so we're going to keep track of what we see in Tim's materials in GeoGebra. So then we're going to have the polygon, the number of sides, the number of triangles, and that will make sense in just a minute. Ugh. And then the interior angle sum. Okay, and we'll talk about how we can use this to make a formula in a little bit. So we're going to come down to doing basically n number of sides. Oh, I should actually put this right here, n, and we call that an n-gon. We will talk about a triangle, a quadrilateral, a pentagon, hexagon, heptagon, and an octagon. I highly recommend you get this table in your notes. I like to ask questions about this property specifically, so be ready for that. The number of sides, we know that a triangle has 3, quadrilateral has 4, pentagon has 5, hexagon has 6, heptagon has 7, and an octagon has 8. And then we're getting to the n-gon after that. Okay, and the number of triangles and interior angle sum, we haven't gotten that yet. So let me get back to this tool. And all we're going to do is we're going to follow what Tim shows us using this slider. Okay, so note, here's a triangle. Okay, so I go back to this tool here and I put the number of triangles. Well, there's only one there. Okay, and he has colored what we call the interior angles. Notice that they're the angles on the inside of the polygon. And so I'm going to slide them over. So this is just a tool. And so I want you guys to note that by taking the colors, we are talking about the size of these angles, okay? And when we put the size of the angles together, that means we are taking the sum, okay? So this is the interior angle sum of the triangle. And when I put them together, they make a straight line. That means that my interior angle sum, well, you should know that the interior angle, when we have a straight line, the angle measure is 180 degrees. Okay. So let's move on. Looking at a quadrilateral now. It's going to do the same exact thing. So I'm going to take it and note, this time around, it's like we're doing the same approach, but we're only taking part of these angles. And you can actually even see a line cutting this figure. Okay, so there is a line cutting this figure down this diagonal. And you'll see that more in just a second. So there is one triangle with 180 degrees for that angle sum. And then there is a second triangle right here with another 180 degrees. So what we're going to do is we're going to come in here. We ended up with 2 triangles inside of this quadrilateral. And the interior angle sum, all of those colored angles would be 180 times 2. Which we should know, is 360 degrees. Let's not make any observations yet. Let's move on to the next one. All right, let's talk about the pentagon. Okay, so I'm going to begin the slider. We've added up 1 and ended up with a triangle. That means that that portion of my interior angles, that colored portion, is 180 degrees. I'm going to do it again. And that's a second triangle with 180 degrees. And then a third triangle with 180 degrees for all of those angle sums. Meaning that I had 3 triangles inside, and my interior angle sum, all of the colors, is 180 degrees 3 times, which I believe is 540. Let me actually do some lines. I'll pause the video and do lines in just a minute. Okay, let's go on to the next one. And hopefully you guys can start guessing what's going to happen here. So I'm going to slide this over. One triangle with 180 degrees. Two triangles with 180 degrees. Three triangles with another 180 degrees. And then four triangles with 180 degrees. So we ended up with 4. And the interior angle sum is the 180 degrees. Oops, that's supposed to be a 4 there. 4 times. And that would be, let's see, 8 times 4 is 32, so 720. And you know what? I'm going to actually go ahead and come in here and put down times 1 equals 180 degrees. Just for continuity's sake, I like to make sure that everything matches. That's what continuity is that everything is this, has a flow, continues. All right, then the heptagon, which is my 7-sided figure. I'm going to do it a little quicker. 1, 2, 3, 4, and 5. So I had 5 triangles, and my interior angle sum is 100. Ooh, that is ugly. There we go. It's 180 degrees 5 times. So that gets me, let's see, so 8 times 5 is 40, isn't it? Oh, 900. There we go. Moving back to do one more figure, our octagon. Okay, so I'm going to go 1, 2, 3, 4, 5, 6 triangles, and that interior angle sum is 180, 6 times. And so I end up with 1080 degrees. So I want you guys to pause the video and take a guess as to what the n-gon would look like. And I'm going to just clean this image up real quick. It's a little messy. So pause your video. Ugh. Okay, I should have paused my video. Sorry. Okay, either way, it's just going to be messy apparently. So the number of triangles is actually going to be n minus 2, because each of these I subtract 2 to get the next image. Minus 2, minus 2, minus 2, minus 2. I said to get the next image, I meant to get the number of triangles inside. And that actually has to do with the way you make a triangle. So if this is my figure, my very crooked figure, and I'm just going to pick one vertex. Well, this vertex is already connected here, so I'm not going to bother with that one. So I'm not that one. And it's already connected here, so I'm not going to bother with this one. But I can connect to this one right there. And look at that, I got a triangle. Okay? And I can connect to this vertex here. And so that's where I end up with my 3 triangles. I skipped out on 2 of them because they were already connected. So that's why I subtract 2. Okay? Just making that explanation as to why it's minus 2. And this formula here, if I go through and highlight everything, that says marker, I hope it's like a highlighter. Yeah. If I highlight the numbers that change, that matches these numbers here, which means that my formula should have the format 180 times n minus 2, because that's the same thing. So this is the formula for the interior angle sum of convex polygons. I really like to ask this on a test. How do you create the formula given a set of polygons? So I'll say part A, which polygons will you use? And if you tell me something like this, that's supposed to be 5. 6. If you do that and then do some dots, that's great. And I'll say, well, what do you do to these figures? And you're like, okay, well, this one stays the same. And then this one gets a triangle. This one gets, oh, that's messy, but it gets 2 triangles, or 3 triangles. Or diagonals cuts in there, you know. This one here gets some cuts. I do that. And then, you know, I ask from there, how can you make this formula? And if you understand this, you know how to do that part of the test usually. I'll give a variation because I just told you guys all this stuff, but you really want to make sure you understand how this formula works, okay? I'm gonna ask you to pause the video and get this down if you need it. I'm gonna give you 3 seconds. Okay. And then let's go back to Tim's resources on GeoGebra because we want to talk about a different property. Actually, let's write down what the property is first. So we want to figure out the exterior angle sum of a polygon. And this is again a convex, no caves. Okay. So this one, yeah, that's all we need to write for that part. And let's go back to the triangle. Let's say we want to say show exterior angles. So let's see what he does. You know what? I don't like the way that one looks. Is this the one that I like? No. Let me pause the video and find the one that I do like. Give me just a second. Find my pause. Okay, still sticking with Tim's resources, but he calls it the exterior angles revisited. He's done this multiple different ways. Okay, so this one, we're going to start with the triangle, and note these angles that you see here. This is how you would create exterior angles for a figure. So let's say I gave you a hexagon, okay, and I wanted you to make the exterior angles. What you would do is you'd pick any side, and you would extend that side. Man, that's supposed to be way straighter than that. And then you'd go to the very next side in the direction that you extended it and extend in that same direction. Pick that next side in the same direction, you extend. The next side, you pick that same direction and you extend. You do not make the extension go in both ways for that side. So if you did this, you would be wrong. That would not be the exterior angle. That's too much. You need to pick one direction and go along that direction for all of the sides. And so once we've done this, then you'll notice that you've got angle here, angle here. These are your exterior angles. Okay, so going back to the resources with Tim on GeoGebra, I'm going to make the slider go, and notice this time around is taking the exterior angle color, meaning the size, and it looks like we're going to put them together again, which if we're talking about the angle, oh, he doesn't say angle sum, we're talking about the exterior angle sum, so we're going to put those two exterior angles together. That's what summing does, and it makes a full rotation. Let's try that again with a quadrilateral. And notice I can actually slide my angles and I can move this around, which, oh, that doesn't look right. So let me try doing this with that. Oh, that's so strange. Why doesn't that work whenever it's got a cave in it? Anyway, sorry, so let me put it back. So let's say this is my figure. It should still hold. Look at that. It makes a perfect rotation of angles, or like a full rotation. All right. So let me move this just a little bit just so you guys can see that this can be moved. I'm going to slide these and they make a perfect rotation again. Notice that it's like a camera shutter. That's where the lens would be, and the camera shutter closes in on the lens to cover it up. Makes that full rotation again. And then here we have a hexagon. That's as far as we're going to go in terms of polygon number of sides, because every single time it makes one full rotation. Well, if that's the case, here is half a rotation, and we know that's 180. If I went one more half rotation and get 180, that gives me a total of 360. So that means that for any convex polygon, my exterior angle sum is always going to be 360 degrees. Okay? Give you a second to get that down while I pause and move to my next resource. Okay, the next topic I want to hit on, and I think it's actually oh no, it's the second to last topic for this one. So I know this video is long again, but it's a full lesson's worth, that's why. So we're talking about congruency. And the definition that you should remember from high school, from middle school, last time you heard this term, is same size, same shape. Okay? And I want you to think about how we mark down that something has the same size or something that has equal size. And then shape is like a squiggle, okay? So if we put those together, those two symbols can represent congruency. So if I put them together, same size and same shape, this is actually how we mark off that things are congruent. So if I said that, let's say, segment AL is congruent to segment BM, then I would use this symbol to note that, to say that they are the same shape, of course, they're segments, and that they are the same size, okay? And so let's talk about how you mark that off with segments. I'm sorry, I'm showing you lines. I don't know why I scribble it out as if I'm working with a pen on paper. So let's say I wanted to mark off that those are the same. I wanted to mark off that those are the same angles, angle measures, or congruent angles. Let's say I wanted to mark that, oof, that's a mess. Let's undo that. I have no way of doing that properly, but let's say I wanted to show that those were the same. And then let me add in two smaller segments and then two smaller angles. Okay, so I want to mark that these two segments are congruent. I put a little slash through them. I may have actually shown you guys this in the last video, but I'm just going to revisit it just in case. And then I want to mark that these two angles are congruent. So I put a little arc through them. Now I have these two segments here. If I just put one line on each of them, then I'm saying that all four of these segments are the same. That's clearly not true. So I'm going to put, I'll put two lines here and two lines here. That means that these two are congruent, but not congruent here. The same holds for angle measures. I can put two arcs here and two arcs here to show that these are congruent to each other, but not congruent to these angles. So let me mark off that these are congruent. Angle, angle, 1, 2, 1, 2. This gets to be quite a bit to mark off, by the way. 1, 2, 3. And then something that we can do in alternation is do an arc with little marks through it. So I'm showing that that is a 4. So those are the same. With the I don't know why my computer just did that. Sorry. With the polygon. Oh, where's my pen? Where's my pen? Let me pause my video. I don't know what's happening. Okay, my pen has died, so we're gonna try and do. Let me unplug it. There we go. That should be the last time it makes that noise. Sorry, I hope that wasn't too loud for you. So we're gonna patch our way through this, and I'll show you the slideshow for the rest of this. But these are my ways of showing that these are congruent. If I wanted to do, let's say, so I showed you how to write down that my segments are congruent. I'm going to use my mouse to write this out, so it's going to be really messy. Please bear with me. So let's call this angle A and angle B. So I'd say angle A is congruent to angle B. And if I wanted to talk about the angle measure, so let's call this X and this Y, and I wanted to say that X and Y are the same angle or same measure, I'd say the measure of angle A equals the measure of angle B. And that has to do with the fact that I'm not talking about the whole shape of it. I'm only talking about the size. So that's why I dropped the congruent part of it. Okay? All right, and then the polygons, we wouldn't draw a shape for those ones. We would just say, I'm just going to make up letters here. Let's say this is, and I don't want to write them all in because it's going to be really messy. A, B, C, D. And let's say that's the name of this shape based on the coordinates. If you hear snoring in the background, I'm sorry, that's my dog. He's kind of a loud snorer. Is congruent to E, F, oh, so messy. G, it's like a kid's doing this. H. And that would be this shape here. Pretend that those coordinates are written. Oh, and I have to mention something else too here. So this is A. If I'm saying that A is congruent, A, B, C, D is congruent to E, F, G, H, that means that I'm saying that A is congruent, or that angle A is congruent to angle E. So I can't put down that this is H. Like, that means that A is congruent to H, and that means that this whole order needs to change. So you got to watch out for the order that you write down these names in, okay? That's not going to come up too much in y'all's problems, though. All right, so let's shift to the slideshow. I don't really like this one as much. It's got good pictures, but I can't interact with you in the same way. Okay, so we have regular polygons. That's the next thing we're going to talk about. It's when all the sides are equilateral, which is a term that you need to know, and equiangular, meaning all the sides are the same and all the angles are the same. And then there are definitions for a bunch of different figures here. You need to get these definitions down. That is just part of the studying for this chapter anyway, and that's what I expect whenever you're doing any chapter, is that you're getting the vocab. And you need to be able to recognize those, especially because there is a hierarchy among the polygons. So basically, underneath the quadrilateral umbrella, that's where it gets really, so sorry about that. That's where it gets really scaffolded. And if you'll notice, a quadrilateral can be broken into two different types based on your textbook, a kite or a trapezoid. Kites have no parallel sides. Or at least they start off with, they can have no parallel sides. A trapezoid has at least one pair of parallel sides. And I don't like it. I don't like the way your textbook does this, because it says at least one pair. I've never seen any other textbook say that. Most of them will say trapezoids only have one pair of parallel sides. I don't know why your textbook thinks that it's at least. And the thing is that if it's only one pair, then parallelograms are totally separate. But your textbook says parallelogram is a type of trapezoid, because this one has two pairs of parallel sides. and then it goes from there. If you have questions about this hierarchy, if you feel like you don't understand why the rhombus is underneath the kite and underneath the parallelogram, talk to me about it. I'd love to go over that with you. I'd love to talk about it. Rotations and symmetry, I don't talk about that really. Not in this class. You'll get enough of that in other courses. So I hope that this has been instructive for you. I know that it's a very long video again. I'm trying to keep it short. I love talking to you. No. So anyway, let me know if you have questions. Make sure that you take notes as you go through. And if you didn't take notes as you went through, you need to go back and take notes. Okay. Have a good one, guys.